Okay, let's unpack this. Welcome back to the Deep Dive. Today, we are undertaking uh, a pretty critical mission, diving headfirst into one of the most powerful and, frankly, revolutionary areas of modern AI, graph neural networks, or GNNs.
Right, and for so long, machine learning was really, really good at handling neat, fixed data. Think of a perfect spreadsheet.
Rows and columns, everything isolated.
Exactly. And that works for a lot of classical problems. It really does. But if you actually look around, the real world, the complex, messy, interconnected world, it just isn't organized like that at all.
No, it's fundamentally built on relationships.
It's all about networks, social connections, chemical bonds in a molecule, supply chains, financial transactions, or even what you buy with what on Amazon.
And the moment you realize that those relationships are the crucial data, you need a different tool. And that's GNS.
They're that revolutionary tool, designed specifically to analyze that relational structure.
So our mission today is pretty straightforward. We're going to transform these sometimes complex GNN concepts into understandable, functional building blocks. We want you to walk away understanding exactly how these models can detect hidden patterns, how they predict outcomes.
From flagging spam reviews all the way to suggesting product bundles.
Right. And even how they can generate brand new possibilities, like entirely novel drug candidates. I have to start with this anecdote from the source material that it framed the whole subject for me. It's the preface about the LinkedIn visualization.
Oh, yeah. That's a great one.
The author saw his whole professional network visualized as this huge, sprawling structure. And what was genuinely surprising wasn't just seeing the dots and lines, it was realizing that the clusters, the tightly knit groups he belonged to, they emerged organically. They weren't built on metadata that LinkedIn explicitly stored, like your job title or location. They arose purely from the underlying connections, from the lines between the nodes.
And that's it right there.
That ability to see structure just emerge from connectivity,
Yeah.
that's the power we're diving into.
It really captures the essence of graph analysis. And, before we can analyze that structure, we have to define our fundamental building block, a graph.
The basics.
A graph is essentially a data structure built on two core components. First, you have the elements, which we call nodes or vertices.
The dots.
The dots, and then you have the relationships between those elements, and those are the edges or the links.
The lines.
Correct. But here's the crucial part in the context of GNNs. It's not just about the structure. Every single node also possesses additional feature data, node-specific information.
So, like a person's age or location in a social graph.
A person's age, yeah. Or the atomic number of an atom in a molecular graph. It's the combination of those node features and the structural context, the who's connected to whom that GNNs leverage. They're learning representations that integrate both.
Okay, so let's start with a classic example of why that traditional tabular analysis, why it eventually hits a wall, the iconic Titanic dataset.
A great starting point.
Historically, it's analyzed as a table, right? Age, gender, passenger class, survival status, fixed rows, fixed columns.
And you run a classification model, maybe a simple logistic regression, and you get certain predictive results. It works, to a point.
But you're missing the relationships. You miss the depth that could completely alter those predictions.
That is the key limitation. When you transform that standard tabular data into a graph, you suddenly reveal these rich, unexplored relationships that they don't exist in a spreadsheet.
So the nodes aren't just passengers anymore.
No. They can also represent entities like cabins or family units or even groups defined by shared ticket numbers, which implies some kind of shared economic or social link.
And the edges. They connect passengers who are family members or who shared a cabin. You're inferring these social ties that must have played a huge role in who survived.
Precisely. And what is that transformation bias? It adds this meaningful, predictive context that is completely invisible in a flat spreadsheet.
So understanding who traveled together provides crucial context on survival rates.
Of course. Traditional models only know that passenger A has a certain age and gender. A graph model knows that passenger A is connected to 3 other family members, and oh, by the way, 2 of them survived. That's powerful information.
So the graph structure provides the mechanism for that information to flow, that message passing we'll get to, which is crucial for tasks like node prediction.
Yeah.
You can predict a passenger's survival outcome based not just on their own features, but on their families.
Exactly. The graph allows the model to capture the idea that the survival of one person is not independent of their direct neighbors. It's a relational problem at its core.
Okay, That makes perfect sense conceptually. But then there's the practical problem.
Yeah.
If the graph is so complex, maybe millions of nodes,
Hmm.
how do we physically feed that structure into a standard machine learning model? Because things like random forest or XGBoost, they still only accept vectors, lists of numbers. That's where the concept of graph embeddings comes in, right? We have to squeeze all that complexity into a manageable numerical form.
We do. We need a numerical representation, an embedding, that retains the essential information about where a node sits in that overall structure. A great early technique for this is Node2Vec, or N2V.
Which was inspired by Word2Vec in language processing.
Directly inspired.
Yeah.
In NLP, Word2Vec learns a word's context by looking at its neighbors in a sentence. N2V does the exact same thing for nodes, but it does it by simulating many, many random walks through the graph.
I love the analogy for this. It's like a rumor spreading, or someone just exploring a city. If you repeatedly take paths through an environment, you start to notice similarities. The architecture in one neighborhood, the types of people in another. N2V is basically mapping that context into a numerical space.
A 128-dimensional vector space, typically. And you can control exactly how it explores that neighborhood using a few key parameters. First, you have the size of the embedding.
Which is how detailed each node's profile is, how many traits you're writing down.
Exactly. 128 is a pretty standard number that balances cost with expressive power. Then there's the length of each walk, which is how far out you explore, typically around 80 steps.
You do this hundreds of times for each node.
You do. And the really interesting knob to turn, the one that makes N2V so flexible, is that parameter Q. This controls the trade-off between exploring your immediate vicinity and jumping really far away.
So it's the difference between a breadth-first search, or BFS, which sticks to nearby nodes, and a depth-first search, or DFS, which goes exploring.
That's right. If you choose BFS, you're focusing on nodes that are tightly clustered. Your immediate family, your direct work team, you're capturing what we call structural equivalence.
But if you choose DFS, you're looking for nodes that might be far away structurally, but serve a similar function.
Yes, like two different department heads who never interact directly, but they both act as bridges between big community clusters. That tunable exploration is vital. And it leads us right to why GNNs often outperform traditional models, even when you start with the same embeddings.
Okay, let's illustrate that with a political book's dataset case study. The goal here was pretty simple. Predict the political orientation, left, right, or neutral of books based purely on a co-purchase network.
So the edges connect books that are frequently bought together.
Exactly. So first, the researchers took those N2V embeddings, those static 128-dimensional vectors, and used them as input for a traditional random forest classifier.
And that model, which just relies on those static inputs, it achieved a solid 84.52% accuracy. That's a great baseline.
But then they compared it to an end-to-end GNN model that also started with those N2V features, and the GNN got 88.99% accuracy.
A 4+% jump. That's substantial in this field.
So what's the difference? Why the jump?
That difference is the absolute key takeaway here. Think about the two processes. For the random forest, the embedding generation and the classification are separate steps. The embeddings are static. They never change.
They're just fixed inputs.
Right. But in the GNN model, the embeddings are being updated while the model is predicting the labels. As the GNN learns from the labeled books and updates its weights, it dynamically updates those node embeddings, making them more and more relevant for the classification task.
So the GNN doesn't just use the context. It actually learns to optimize the context for the specific job it's trying to do.
Precisely. It's adaptive. And this leads us to a really critical philosophical distinction in graph learning. When do you train a model on the entire graph you have versus when do you need a model that can generalize to new data it's never seen before?
This sounds like a huge decision point for anyone actually building one of these.
It's the difference between transductive and inductive learning. A transductive model uses the entire graph structure, all the nodes, labeled and unlabeled to do its job. It's completely contextualized by that specific network.
Which means it's great for problems where the whole structure is known and fixed, like community detection in a social network.
Yes, exactly. It's better for maximizing your insight into the current data. It uses every single connection to find those communities with really high fidelity. But if a new user joins the network,
The model is stuck.
yeah,
It has to be completely retrained on the bigger graph to understand that new person's context.
which is computationally prohibitive if you have data streaming in constantly.
Right.
And that's where inductive models shine. They're trained on a labeled training set, And they learn the rules of connectivity. A perfect example is email scam detection.
Okay.
You train an inductive model on a bunch of labeled emails, and then it can instantly classify a new incoming email as spam or not without retraining.
Yeah.
Retraining a transductive model every time a new email arrived would be, well, it'd be impossible for a real-time system.
So the choice really depends on the application's demands. Are you maximizing insight now, or do you need to generalize to the future? Here's where it gets really interesting. So we have our graph. We get why we need dynamic embeddings. But how does the model actually process all that relational information? How does the information physically flow from node to node?
This is the core operational concept of pretty much all GNNs. It's a framework called message passing.
Okay.
It's an iterative process. It updates each node's feature representation layer by layer by essentially blending a node's own information with its neighbor's information.
It's a three-step dance, right? Step one is collect. The central node gathers all the features or messages from its immediate neighbors, everything one hop away.
Step 2 is aggregate. And this is the crucial transformation step. The model combines all those messages it gathered using what we call an invariant function.
Invariant meaning it doesn't matter what order you process the neighbors in.
Correct. The result has to be the same. The output depends only on the set of neighbors, not some arbitrary order. Common functions here are things like sum, max, or mean.
And finally, step 3 is update. That aggregated message is then used to update the central node's own feature representation. This new embedding now captures both its original info and the context of its neighborhood.
And this happens simultaneously for all nodes across the whole graph, and it repeats for every layer in the GNN.
So the number of layers in the GNN is basically the number of message passing steps, the number of hops.
That's a perfect analogy. A two-layer GNN means the final embedding for any node has pulled in information from nodes up to 2 hops away. That defines the size of its neighborhood.
Okay, let's apply this to a huge high-stakes business problem. Predicting product categories on Amazon.
A great case study.
Imagine you're a product manager. Your job is to find emerging trends in product bundles using Amazon's co-purchase network. This is a classic node prediction problem. Predict a product's category based on what it's bought with.
And this is where we really confront the challenge of scale. This data set it's a massive graph. Roughly 2.5 million nodes of products and nearly 62 million edges or co-purchases, all spread across 47 different product categories. And the initial node features were themselves complex. They applied PCA to bag of words from the product descriptions to get 100 features for each product.
So to tackle that kind of scale, we introduced the first two big convolutional GNN architectures. GCN, which is Graph Convolutional Networks, and Graph Sage.
Right. They're both convolutional because they're applying a filter that aggregation function over a local neighborhood, kind of like image convolution. The main difference is in how they handle that message aggregation.
How so?
Well, GCN is what we call spectral-based. Its aggregation includes specific mathematically derived elements to normalize the neighborhood information. The key things are symmetric normalization and self-loops.
Okay, can you break down symmetric normalization? Why is that necessary?
It's basically a defense mechanism against really popular nodes, high-degree nodes, from dominating the information flow.
Like a celebrity in a social network.
Exactly. Imagine a node with 1 million connections. If you just summed up its features without normalization, its popularity would completely overwhelm the features of its less connected neighbors. Symmetric normalization divides the incoming messages by a factor related to the connectivity of both the sending and receiving nodes.
So it scales things down to ensure a fair conversation.
That's a great way to put it. It ensures a fair conversation. Graph Sage, on the other hand, is a spatial-based method. It's generally more flexible and scalable because it leans heavily on sampling neighbors and using simply aggregation like sum, mean, or max.
And since Graph Sage gives us that flexibility, let's talk about optimizing that aggregation step. Intuitively, you might just stick with mean, right? It smooth out the neighborhood. But the source material showed that just changing that one function can drastically change performance.
This was a crucial finding. In the Amazon case study, when they trained Graph Sage with the default mean aggregation, they got an F1 score of about 0.74. But when they switched to max aggregation...
Which just highlights the single most significant feature from all the neighbors.
Right. And the F1 score jumped to about 0.745.
That's fascinating. Why would highlighting the single strongest feature work better than averaging out the whole neighborhood?
It tells us something about the data itself. It suggests that in this co-purchase network, the predictive signal for a product's category isn't spread evenly across all its neighbors. Instead, the signal might be sparse, but really powerful.
So maybe one or two co-purchased items are highly indicative of a new trend.
And max aggregation captures that powerful isolated signal and brings it to the front, whereas the mean would just dilute it. It proves you can't just rely on defaults. You have to think about what property of the graph you're trying to capture.
They even tried to push this further, right? Using a list aggregation that combined max, sum, and mean.
They did, and it provided a slight F1 boost, pushing it up to about 0.748. But, and this is a big but,
There's always a trade-off.
always, that marginal F1 boost came with a significantly higher log loss. And log loss is a measure of how certain or confident the model is. A high log loss suggests that even though it was getting the label right a bit more often, it was much more uncertain about its probabilities.
So it might be right, but it's not confident, which makes it risky for business deployment. You want certainty when you're recommending a $500 product bundle.
Absolutely. From a production standpoint, reliability often outweighs a tiny bump in raw accuracy.
Now, when training these big models on a data set like Amazon, a classic deep learning problem popped up right away: overfitting.
Of course. The training loss drops perfectly, meaning the model is memorizing the training data, but the validation loss starts going up. It's not generalizing.
So the solution here was a regularization technique called dropout.
Yes, they introduced a 50% dropout rate on the hidden layers of their two-layer graph sage model. And dropout works by randomly setting some of the activations to 0 during training. It forces the network to be more robust, to not rely too heavily on any one feature.
And the important nuance for GNNs is that while it's zeroing out the information flow, the dropout operation preserves the graph topology itself.
Exactly. The nodes and edges are still there. The structure is intact. You're just intermittently cutting off some of the information flowing through the connections. This lets the structural learning continue while preventing that over-reliance on specific features.
So the refined Model 2-layer graph sage, max aggregation, 50% dropout, significantly improved performance. And that translates directly into, well, millions of dollars of value through better product recommendations.
Absolutely.
Okay, so we've established that convolutional GNNs are powerful, but they tend to treat all neighbors pretty similarly. Now we move to our second architectural family, one that solves a really common challenge, deciding which neighbors matter most.
Dynamically.
And we're applying this to a very high-stakes domain, detecting spam and fraudulent online reviews.
This is such a critical problem for the trust economy. The statistic is just staggering. Over 90% of adults rely on online reviews for purchases. But Capital One estimated that in 2024, something like 30% of all online reviews were fake.
30%, that's huge.
We need better defenses.
So the source material used the Yelp Chicago Reviews dataset for this. It's a node classification problem. Is a review spam or not spam? The graph has almost 46,000 review nodes and 3.8 million edges.
And the connections are key. Edges link reviews written by the same author or reviews for the same business. The whole hypothesis is that fraudulent reviews will cluster together based on suspicious behavior.
And right away, there's a huge challenge. This is a highly imbalanced data set. Only 14.5% of the nodes were actually fraudulent.
That's the class we're trying to detect. If a model just guessed not spam every single time, it would be right over 85% of the time. So we need to be much, much smarter than that.
The richness here comes from the 32 node features, which are designed to highlight suspicious activity. They're split into two types: behavioral and textual.
Yes, and the behavioral features are crucial for spotting automation. For example, one feature is the maximum number of reviews written by a single author in a single day. If a person writes 100 reviews in 24 hours.
But that's a bot.
Yeah.
Or a paid reviewer. It's not normal behavior.
Highly suspicious. And the textual features target the language itself. Things like the percentage of all capital words, which tends to be high in fake reviews, or the review length. Very short reviews are suspicious.
There was another fascinating one: the ratio of first-person pronouns, like I and my.
Right. Low values there are often suspicious because fake reviews often try to sound objective, or they're just generically written, avoiding any personal story. So these 32 features are the inputs the GNN has to learn to weigh.
Which brings us to the Graph Attention Network, or GATE. We said GCN treats neighbors similarly. GATE is the solution.
It's essentially a simple but brilliant extension of the GCN architecture. It just replaces that static aggregation operator, that hard-coded sum or mean, with a sophisticated attention mechanism.
So instead of being forced to listen equally to every neighbor, the attention mechanism is trained to learn which messages it should pay the most attention to.
Yes. In context, during training, GAT assigns a learned dynamic weight to each neighboring node's contribution. It amplifies relevant features and suppresses irrelevant ones. For this Yelp data, it might learn that a neighbor's max reviews per day feature is way more important than their average review length.
And we even see a refinement called JET-TV2 Conv used here. What's the improvement there?
The original GAT had a slight limitation where the attention weights were static within a single layer. JAT-TV2 makes the attention mechanism dynamic across layers, which allows for more expressive weight learning throughout the network. It can capture more complex relationships.
But as you said before, there's always a trade-off. GATs offer higher performance, but what's the cost?
The cost is always complexity and time. Calculating all those attention weights takes significantly longer to train, and it can reduce scalability for extremely large or dense graphs where calculating attention for every single connection becomes computationally prohibitive. You're trading speed for precision.
And speaking of challenges, this specific problem fraud detection has that massive structural hurdle of class imbalance. As you said, only 14.5% of the data is the fraud we actually care about finding.
This is a classic machine learning trap. A model can get a stunningly high overall accuracy just by being great at identifying the majority class, the non-spam.
So it looks good on paper, but it's failing at its real job.
And that's what happened initially. A deeper analysis showed the GATV2 model really struggled with precision and F1 scores when compared to a non-GNN XGBoost baseline. That baseline, which only used the tabular features and ignored the graph structure, got an accuracy of 89.25%.
Wait, hold on. A non-GNN model that ignored all the relational context performed better than the GATV2. That seems to go against everything we've been saying.
It highlights the challenge perfectly. The sheer volume of legitimate reviews just drowned out the fraudulent signal. The GNN was optimizing for overall accuracy, which meant just classifying everything as not spam most of the time.
So the solution wasn't just in the model architecture, but in the data pipeline itself.
Oh.
You have to force the model to care about that tiny minority class.
That's where a technique called class reshuffling comes in, using something like a balanced node sampler.
And what does that do?
It addresses the imbalance directly during training. It ensures that when you create mini batches of data to train on, each batch contains equal or near equal portions of the majority and minority classes.
So if my batch has 100 nodes, 50 will be legitimate and 50 will be fraudulent, even though that ratio is totally skewed in the real data set.
That's the idea. You're artificially increasing the model's exposure to the rare positive class. You force it to learn the specific features of the fraudulent nodes. And applying this strategy significantly improved the GATV2 model's performance, proving that GNNs can overcome these challenges when you couple them with smart sampling methods.
So architecture alone can't fix a fundamental data problem.
Never.
Okay, we've covered discriminative models. Models focus on learning how to separate classes. But now we shift to something fundamentally different. Models that learn how to generate data. This feels like a whole other level of intelligence.
It is. Generative models aim to learn the underlying data generating process itself. They learn how to build the graph. And the foundational architecture here is the graph autoencoder, or GAE.
So an autoencoder has two parts. An encoder, which is a GNN that compresses the complex graph into a simple, low-dimensional representation called the latent space.
And then a decoder, which tries to reconstruct the original graph structure from that compact latent space representation.
And the most common application for GAEs is link prediction.
Vital for recommendation systems. Let's go back to that Amazon co-purchase network. A GAE's job here isn't to predict the product category, but to predict where a new item should be placed in the network. It's predicting new edges that should probably exist.
So it can suggest product bundles that shoppers haven't even discovered yet. How well did it do?
The standard GAE model achieved an overall test accuracy of 86% for edge prediction on the Amazon data, which is a really robust performance. It means the model can suggest a meaningful co-purchased item 86% of the time.
But GAEs have a limitation when it comes to true generation of novel data, right? They're deterministic. Each input graph maps to one single point in that latent space.
Right. And if you try to create something brand new by just picking a point between two existing points, you can get sharp discontinuities. It's the flying boat analogy. You interpolate between a car and a plane, and you might get something that's neither functional nor real.
That is the exact problem the variational graph autoencoder, or VGAE, was designed to solve. It introduces a crucial element. It transforms that latent space from just a collection of points into a well-structured probabilistic density.
a smooth field of possibilities.
And how does it force that structure?
It uses a special mathematical measure called Kullback-Leibler divergence, or KL divergence, as a regularization term in its loss function. It doesn't just ask the decoder to reconstruct the graph. It simultaneously forces the encoder to make sure the distribution of encoded points looks like a simple, predictable distribution, usually a standard bell curve.
So it's not enough to just compress the data. The compression has to be organized into a smooth, recognizable probability field.
Exactly. So now there are no flying boat discontinuities. You can sample a new point anywhere in that smooth space and reliably generate a corresponding new realistic graph. If your goal is truly to generate new data, VGAEs are far superior.
And on the Amazon Link prediction task, the VGAE achieved 88% accuracy, which is slightly higher than the GAE. But the real win is that reliable generative power.
Which has had a massive, tangible impact on the field of drug discovery.
It's been transformational.
We saw the discovery of a new antibiotic using GNNs back in 2020 and new methods for identifying carcinogens. The ability to model these structures is driving huge advances.
So how do you actually represent a molecule as a graph?
Molecules are naturally perfect little graphs. The individual atoms are the nodes, and the atomic bonds are the edges.
And those graphs are often heterogeneous because the bonds can be single, double, triple.
Exactly. Multiple types of relationships existing at the same time. The graphs themselves are usually pretty small, fewer than 100 nodes.
So how does the VGAE architecture help us search for new drugs, which is an optimization task?
We use the VGAE to do what's called property-guided generation. The goal is to generate new chemical candidates that have a high score for a specific desired property, like QED.
Quantitative estimate of drug likeness.
Right. It's a measure of how likely a compound is to be an orally available drug. It balances things like molecular weight, solubility, and so on.
So the VGAE is trained to learn how to encode both the molecule and its QED property into that smooth, latent space.
Precisely. Once that structured representation is learned, we can essentially walk through the latent space using optimization techniques like gradient ascent to find the coordinates that correspond to new, never-before-seen molecules with a high QED value. We're guiding the generation toward a desirable outcome.
But to actually synthesize a whole molecule, not just predict a property, the model has to do more than just predict a link. It needs to generate the whole thing from scratch.
Yes, the complexity there increases significantly. The decoder has to be trained to output the entire structure of the molecule. It has to generate both the entire adjacency matrix, all the bonds, and the feature matrix, all the atom types. That's the highest level of complexity in generative GNNs.
So we've covered the three major families of GNNs. Now we have to tackle the real-world headache of data science scale. We saw the Amazon dataset was huge, 2.5 million nodes, 1.3 gig zipped. For a company like GeoGrid, dealing with nationwide road systems or disease spread, this problem is constant. You just can't load the whole graph into memory.
Yeah, these graphs can get into the billions or even trillions of nodes. And when you're dealing with that kind of scale, you have to understand algorithm efficiency. You have to understand big O notation.
That mathematical shorthand that tells you how an algorithm's runtime or memory usage will grow as the input size grows.
And you have to care about it. We see complexities from constant O, which is amazing, to logarithmic N, to linear, all the way to really slow quadratic art. You can't train on massive graphs if the complexity grows too quickly.
This is why the architectural choice matters so much.
It's critical. GCN's time complexity is related to the number of nodes and features. It's fine for moderate graphs, but you have to load the whole thing. But GraphSage, because it's spatial and flexible, it allows for neighbor sampling.
Right.
And when you incorporate sampling, GraphSage is often preferred for large graphs because its spatial approach gives you much better time complexity when the number of nodes is massive. It avoids iterating over that entire adjacency matrix at once.
So what are the main techniques for tackling scale when that full batch approach is just impossible?
The first and most common is sampling and batching. Instead of training on the whole graph, you sample a subset of nodes or subgraphs for each training iteration. You move from an impossible full batch to a manageable mini-batch approach.
And how does that sampling actually work in practice?
There are tools specifically for this, like the neighbor loader in PyTorch Geometric. When you're training on a mini batch of nodes, the loader samples the neighbors of those nodes for the first hop, then the neighbors of those neighbors for the second hop, and so on. It approximates the full convolution by only loading the necessary subgraph.
It's a huge memory saver.
Enormous. Second, for really extreme scale, if you have the hardware, you use distributed processing, or DDP.
Training a model across multiple GPUs at the same time.
Right. GeoGrid considered this for a high-stakes government project where speed was everything. It offers huge speed gains, but the engineering overhead is massive. You have to manage all these synchronization points to make sure the GPUs agree on the updated weights.
The third technique, which GGrid used really creatively, is graph coarsening. This is a structural solution.
Yes. Coarsening means reducing the graph size by merging or aggregating groups of nodes into supernodes while trying to preserve the essential patterns. For GeoGrid, modeling the nationwide road system, they realized that maybe not every single minor road junction needed to be its own node.
But what happened when they just tried to coarsen the entire national grid?
It failed because they lost too much critical detail. Imagine merging all the streets in a major city into one single supernode. You lose all the local routing and traffic insights. The model became inaccurate.
So what was the breakthrough?
The breakthrough was implementing a multi-layer framework, national, state, and city levels, and they applied graph coarsening only to the intermediate state level.
Oh, okay.
This gave them the computational efficiency they needed for modeling large regions without destroying the local detail at the city level.
So the city level kept its fine granularity, the national level provided the global context, and coarsening the state level was the efficiency layer in between.
Precisely. The city and national layers acted as checks, mitigating the inaccuracies introduced by coarsening that intermediate layer. It was a perfect balance of efficiency and data integrity.
Okay, finally, let's move beyond static graphs to systems that are fundamentally dynamic, the ones that evolve over time. The challenge here is modeling temporal data.
Right. The case study for this is the CMU Motion Capture Database, which tracks complex human motion. It uses 41 sensors on a person's joints as they're walking or running, and the goal is pose estimation, predicting the future position of the nodes, the joints, without even having predefined edges.
Because the functional graph which joints are moving in relation to which other joints is dynamic. It has to be inferred.
This requires a really complex hybrid architecture. The model used is called Neural Relational Inference, or NRI.
How does that work?
It's a dual system. First, an encoder predicts the edge probabilities. It learns what the latent graph structure should be at any given moment. It infers that the elbow is connected to the shoulder based on the movement data.
And then the second part.
A decoder, which uses a recurrent unit like a GRU, combines those inferred edge probabilities with the past trajectory data to predict the future time steps, the future pose.
That's fascinating. The model is essentially inferring the physics of the system, the connectivity rules, and then using that inferred structure to predict what happens next.
Exactly. It uses the structural information to improve the time series prediction. Simple RNNs or GRUs, they only got about 60–65% accuracy on this task because they struggle with those long-range spatial dependencies. But the NRIJT model, by incorporating both the spatial graph structure and the temporal GRU memory, achieves significantly higher performance.
So what does this all mean? We started by recognizing that, the world is not a spreadsheet, it's a network of relationships. GNNs are the engine that allows modern systems to model the complex interdependencies that govern everything from product recommendations and fraud protection to predicting new drug candidates.
We've seen the three major families of GNNs in action, each addressing a unique need. The convolutional models, like GCN and GraphSage, for robust local learning. The attention models, like GAT, for dynamically weighing what's important. And the generative models, like GAE and VGAE, for learning how to create new data. But at the end of the day, all of them rely on that core iterative mechanism of message passing to translate neighborhood relationships into predictive power.
It's a powerful and flexible framework, clearly, capable of handling massive static graphs and inferring dynamic ones. But there are always new frontiers.
Absolutely. And we noted throughout this that GNN depth is inherently limited by a critical problem called oversmoothing. After too many message passing steps, the features of all the nodes start to converge. They all look alike. It becomes impossible to tell them apart.
So you can't make them too deep.
Right. But the necessary problem radius, the range of information you need in complex fields like chemistry or biology, can be quite large. You need to model these long-range interactions. So the question for the next generation of researchers is this: how will we design new GNNs to solve this fundamental architectural challenge, to go deeper and unlock the potential of ultra-deep graph learning without making every node in the graph indistinguishable?